in this experiment we're going to determine the purity of a marble sample by a back titration. Now marble is mainly calcium carbonate, which is a base, and so it does react with an acid. So the obvious way to do the analysis is by titration. However, calcium carbonate is an insoluble base, so we can't just dissolve it in water and carry out a titration. So when trying to analyse an insoluble base, it's necessary to carry out a back titration. So in this experiment, we're going to initially add a known amount of hydrochloric acid to our sample of calcium carbonate. It will react and produce calcium chloride solution, carbon dioxide gas and water. Now the hydrochloric acid will be in excess, so there will be some hydrochloric acid remaining at the end of the experiment after we've used up all the calcium carbonate. In order to determine how much hydrochloric acid is left, we'll carry out a simple titration with a sodium hydroxide solution of known concentration. In fact, we'll use the sodium hydroxide solution which is standardised previously in experiment 1. The equation for that reaction is quite simple. The sodium hydroxide and the hydrochloric acid react in a 1-to-1 ratio. So, we know how much hydrochloric acid we started with. We know how much hydrochloric acid was left at the end of the experiment. So the difference between those two numbers gives us the amount of hydrochloric acid that reacted with the calcium carbonate. So the number of moles of HCl that reacted with the marble equals the number of moles of HCl initially added, and we know that because we knew the concentration and volume of the HCl, take away the number of moles of HCl left after the initial reaction between the calcium carbonate and the hydrochloric acid. So that gives us the number of moles of HCl which reacted with the calcium carbonate. So if we know how many moles of that reacted, we know how many moles of calcium carbonate we started with, and hence we can work out the mass and the purity of the calcium carbonate sample. So the first thing we have to do is weigh out approximately 0.8 grams of the marble chips straight into the standard flask. So put the standard flask on balance, zero it, and now because marble is completely harmless, I'm just going to actually use my hand to put the marble chips in here. Normally we wouldn't do this, but this means it's less likely spilling it. So I want to get roughly 0.8 grams. Leave it to settle. So that's close enough. But I record the exact mass we have got, which is 0.83 grams. So my mass of marble chips, 0.83 grams. Okay. Right, the next thing to do is to add 25 cubic centimetres of our standard solution of hydrochloric acid, which is 1 mole per litre. Now the pipette has already been washed out with the hydrochloric acid. I've filled it up to the mark. I'm now going to pipette in the 25 cubic centimetres of my 1 mole per litre. You'll see it starts to bubble because of the reaction between calcium carbonate and hydrochloric acid, which is producing carbon dioxide gas. And what we have to do now is leave it until the reaction is going to completion. So we're actually going to leave this overnight to give time for all the calcium carbonate to have reacted. It's important that you do not stopper the standard flask because we want the gas being produced to be able to escape. So just put that aside and leave it overnight and then continue the experiment next time you can. We can now work out the number of moles of hydrochloric acid added to the marble chips. So it's just the concentration times the volume. Concentration was 1 mole per litre. The volume was 0.025 litres. So the number of moles of hydrochloric acid we added to the calcium carbonate was 0.025 moles. Okay, so this has been left to react overnight, and the calcium carbonate has more or less disappeared. You might still see tiny lumps in your sample. That's because the marble isn't pure calcium carbonate, and there might be some impurities that don't react with the acid, and that's one of the things we're trying to find out. So next thing we have to do is make this up to 250 mils. So I'll add some deionized water. Okay, so we're getting quite close to the mark. So I'm now going to start adding it with a dropping pipette until we get to the exact mark. One more drop. Yep, it says. Stopper it and invert it 2 or 3 times, get a homogeneous solution. So obviously there's less moles of hydrochloric acid left in this flask than there was originally, because some of it has reacted with the calcium carbonate. So what we want to do is find out what the number of moles of hydrochloric acid left in this flask after the reaction, and we'll do that by titrating it with the standardised solution of sodium hydroxide that we prepared for the first experiment. Right, you're going to be using methyl orange indicator, and I just want to show you the different colours of methyl orange. So our solution will start off being acidic. So we get this pinky red colour, and when we reach our end point it should be orange. So you can see the difference between the initial colour and this is the final colour that we'll be looking for. Okay, so to find out the number of moles of hydrochloric acid left in the standard flask, I pipette out 25 mils of the reaction mixture. Having previously cleaned the pipette. Then we add 2 or 3 drops of our indicator, methyl orange. And we get the pinky colour you get in acidic conditions. Okay. I have already washed out the burette and filled it up with our standardised sodium hydroxide solution. So I record the starting volume for our rough titration in my lab book. And then I'll proceed to do the rough titration, and then as many accurate titrations as is required to get concordancy, remembering that at our end point we should see a solution which is more yellowy orange rather than pink. Having done my titration, I know that the average volume of sodium hydroxide required to neutralise the remaining hydrochloric acid was 10.2 cubic centimetres. So using that result, I can calculate the number of moles of hydrochloric acid remaining in the flask after the reaction with marble. So the number of moles of sodium hydroxide, or the concentration, use the concentration you worked out in experiment 1 for your sodium hydroxide solution. In my case it was 0.132 moles per litre. The volume was 10.2 cubic centimetres, or 0.0102 litres. It gives me the number of moles of sodium hydroxide as 1.35 times 10 to minus 3 moles. Now from up here we know that 1 mole of sodium hydroxide reacts with 1 mole of HCl. So the number of moles of HCl was 1.35 times 10 to minus 3 in the 25 cubic centimetres that we titrated. The total solution was of course 250 cubic centimetres, so the total number of moles of hydrochloric acid is 10 times that, so it's 1.35 times 10 to minus 2 in 250 cubic centimetres, which was our entire sample, and that's equal to 0.0135 moles. Right, using these results now, we're in a position to work out the mass of calcium carbonate in the sample and hence its purity. So, in order to work out the number of moles of calcium carbonate, we need to know how many moles of HCl reacted with the calcium carbonate. So the number of moles of HCl that reacted is given by the number of moles we initially added, which we worked out to be 0.025, take away the total number of moles that were left at the end of the experiment, which we've just calculated as 0.0135. So total number of moles of HCl that reacted was 0.0115 moles. If we look at the balanced equation, we know that 2 moles of HCl react to 1 mole of calcium carbonate. So the number of moles of calcium carbonate is half the number of moles of HCl. So the number of moles of calcium carbonate would be 0.0115 divided by 2, which comes out at 5.75 times 10 to minus 3 moles. So the mass of calcium carbonate is number of moles times the GFM, so 5.75 times 10 to minus 3 times its gram formula mass, which is 100.1, which comes out at 0.58 grams. So that was the mass of calcium carbonate in our marble sample. The percentage purity is given by the amount of calcium carbonate over the mass of marble, which in my case was 0.83 grams, multiplied by 100 to turn it into percentage. It comes out at 69.9% pure. So our marble sample was 69.9% calcium carbonate.